Select the major products of the following reaction. If we look at the starting material, we see that we have an anhydride. And anhydrides, similar to carboxylic acid chlorides or acyl chlorides, have a good leaving group. So the leaving group attached to the anhydride, this one is symmetrical, so we can consider either of these carbonyls being where we're going to attack and the other portion as the leaving group. So I'm just going to select one side, although I could have easily selected the other. So when this leaves, it would leave as a carboxylate ion, which is a relatively weak base. So this is a good leaving group. And so the reactivity of anhydrides then are similar to acyl chlorides. And so if you picture that leaving group the same way you picture the chloride leaving group, you'll have a good idea of what happens in this reaction. So let's go ahead and redraw this anhydride. And because you have a good leaving group, this is capable of reacting even with a weak neutral nucleophile like water. And when we're doing a reaction with water, this is going to be a hydrolysis reaction. And so all of your carboxylic acid derivatives can undergo hydrolysis reactions. So anhydrides, acid chlorides can undergo the reaction with just water. Your less reactive carboxylic acid derivatives will require either acid or base. But all carboxylic acid derivatives can undergo hydrolysis to give carboxylic acids. So at that point, we can actually just quickly identify that answer that you're going to get a carboxylic acid, actually two of them as we split them apart. And let's take a look at the mechanism as to how that happens. So we've got that weak neutral nucleophile water. So we can show this attack either one of the carbonyls. And because there's two carbonyls, that's why we tend to see this anhydrides being used as these small symmetrical anhydrides so that you're going to get the same product regardless of the carbonyl that you attack. So I'm just going to attack this one. What's going to happen first is this pi bond then is going to break to put the lone pair of electrons onto that oxygen, giving us the tetrahedral intermediate. So we put an extra lone pair on that oxygen. It now has a negative charge. We have the rest of the anhydride still attached and the water molecule that we just used. And then at this point, we have a lot of water around. It is our nucleophile, it's also the solvent, so we can remove an extra proton here using another water molecule as a base this time to remove that proton, putting those electrons back onto the oxygen. And we will have the next tetrahedral intermediate in the reaction. So there we have it. And at this point, we can see that these pi electrons are going to come back down and they're going to kick off that good leaving group, the carboxylate ion. Right, so we've seen one equivalent of this carboxylic acid form, and we've also kicked off that carboxylate. And if we protonate that carboxylate, we will get the second equivalent. And with this deprotonation step right here, we just generated some H3O+. So I'm going to use that as my acid to put a proton onto this carboxylate. So this can grab a proton. And we have now formed those two equivalents of carboxylic acid.